Okay, in activity 2, we have to use the elimination method to solve this system. So in step 1, they tell us to put it in the general form, which we would need to do anyway without somebody telling us, because when we use the elimination method, it's best to have it in general form. So it looks like things are sort of out of order. In equation 1, I'm going to move the y to the left, and in equation 2, I'm going to move the negative 7x this way and the negative 15 the other way, so I can have it in this general form. So let's do that. So for equation 1, subtract 2y from both sides. 3x minus 2y equals, keep the 13 there. That's good to go, it's in general form. For equation 2, I'm going to add 7x to both sides. That's going to give me 7x plus 3y. The minus 15 is still there, and then I got a 0 on the right side. I don't want the minus 15 there, I want the number by itself on the other side, so I've got 7x plus 3y equals 15. So 1, check, good to go in general form. 2, check, good to go, they're both in general form. Now I'm going to line the x's and the y's and the numbers, and it says to find the LCM, or least common multiple, of the y coefficient. So the y coefficient, I guess we would lean towards eliminating y's anyway, because one's a positive, one's a negative. Since they want us to do it with the y's, we'll go ahead and stick to that. The lowest common multiple between 2 and 3 is 6, so I want both of these coefficients to match up and look like a positive and negative 6. So in order to get a negative 6 up here, it looks like I need to multiply the top by a 3, I guess, all the way through, and the bottom one by a 2 to get a 6 for the coefficient of the y's. So 3 times 3, 9x, 3 times negative 2, negative 6y, equals 3 times 13, 39, all the way through. 14x plus 6y equals 30. Again, we had opposite signs for the y coefficients. We got both of them to look like 6's, so that when I add the two new equations, I can get x. And that's a 14x. So add these guys up. These guys go away. We end up with 23x equals 69. Divide by 23, divide by 23. And it looks like we get x equals 3. So we added the new equations, so we got them in general form. We got the same coefficient for the y's. We finally got the value of x. Now we're going to go substitute this value in to get the y. They want us to use the second equation and find the y value. So I'm going to go back into the second equation. Whichever equation I go back to, even after reordering them, it doesn't matter. But they said go back to the second one, so I'll go ahead and go back to the second one, which says 3y minus 15 is equal to negative 7x. 3y minus 15 is negative 7 times this guy that I just found. 3y minus 15 is negative 21. Add 15 to both sides. Looks like we get a 3y equals negative 6. Divide by 3, and the y value is negative 2. So we got our x, we got our y. The ordered pair solution we think is 3, negative 2. However, so we did this step. The last step, that's not printed on here, says to check the solution into both equations. So let's go do that. Plug in x here, y there, and then again plug the same x here and the y there. So we put x 3, y negative 2 into equation 1. That gives me 9 equals negative 4 plus 13, and 9 equals negative 4 plus 13 is 9, so that's a check. I get a true statement. I've also put in 3, negative 2 into the x and y of the second equation. Let's go simplify those guys. I get negative 6 minus 15 equals negative 7 times 3 is negative 21. Combining the negative 6 and the negative 15, I do indeed get a negative 21 on both sides, so this must be the solution to the system. Part 2 of the activity is pretty much the same as part 1, except we're going to be dealing with getting rid of the x's, so I'm going to show the work quickly. So rearrange equation 1 to get it in general form, rearrange equation 2 to get it in general form. Align x's, y's, and the numbers, opposites, and they want us to find the LCM, least common multiple of the x coefficients. I guess because they have opposite signs to begin with, and we just want to wipe them out. It looks like the lowest common multiple of 3 and 4 is a 12, so I can make them both look like a 12. If I want a 12, then I better multiply everybody upstairs by 4. And if I want a 12 here, I better multiply everybody by 3. So again, my focus is how can I get a 12 for both of these since they have opposite signs anyway. When I multiply them through, x's go away and I get 17y equals 17. So nicely, y must be equal to 1. So we got this done, we got that done. We added the two new equations, we have the y value. Now we're going to go back into the second equation and find the x value. They say the second equation, of course I don't have to go to the second equation. Whichever one I go to, I will get the x value. So we took y equals 1, plugged it back into the second equation, and that led us to get what the x coordinate is, which is 2. So right now the solution we think is 2, 1. But I'm going to go check to make sure that the ordered pair satisfies both equations. So, equation 1, I put in the x and the y, that gives me 6 equals 8 minus 2. That indeed is a 6 equals 6, so it worked in the first one. I plug the x and y into the second one. 3 times 1 is 3, that's an 8 minus 5, and on both sides I do get 3 equals 3, so 2, 1 is the solution to that system. Part number 3, again, we're doing the system, solving it by the elimination method, and if I want the elimination method, equation 1 looks good because it's in general form already. Equation 2 I got to work with a little bit because it's kind of out of order. I want the y on the left, like we did with the other two. I have a 0 left on the right side, and now I want the constant moved to the other side. So I have 2x plus 6y equals 12. Now equation 2 is good to go as well. So let me recopy x plus 3y. So I got x plus 3y equals 6 for equation 1, and equation 2 put in general form is 2x plus 6y equals 12. They want us to use the elimination method, so we could eliminate whichever variable we want. I'm going to go ahead and stick to the x. If I want to eliminate the x, I would like a negative 2 in front of the x as a coefficient. So I'm going to multiply the first guy by negative 2. That means everybody else is going to get multiplied by negative 2 as well. And I don't need to change this guy because it's going to match up with the coefficient as I want upstairs. So this guy is going to turn into a negative 2x minus 6y equals negative 12. Now what happens here is when I add them, these guys go away. These guys go away, they cancel. So I have a 0 left on the left side equals, these guys cancel as well, and I have nothing left on the right side. I get 0 equals 0, which is a true statement. And remember, when you get a true statement and all your variables disappear, that is a dependent system. That means if I were to graph these two guys, they would be identical lines. They would lie on top of each other. If I had gotten a false statement, remember, and the x's and the y's disappeared, then it would be inconsistent, and that would be the case where your two lines don't intersect at all. That's graphically speaking. In other words, these two systems, these two equations create a system that have all of their solutions in common. They're identical. All ordered pairs match up for both of them. So this is a dependent system because I got a true statement.